So welcome back, and this is the last day of the workshop, and this the first talk is again by David Treumann, and his title will go from high dimension to three dimensions, right? So some examples.
Some examples.
Do you want to put on? It's already.
It's already.
By the way,
Yeah.
is there a URL for the recording of yesterday's talk? Because Victor Gilliman wanted to see it, but he wasn't able to come.
Oh, I think it's just you can get the link from this conference, but from the center.
I see.
And
Is it
then,
already online?
No, it takes some time. Yeah.
So yesterday I defined a category. Which is a Lagrangian isotope invariant of Lagrangian. An object of that category is a sheaf on Y. And you can picture that as some vector spaces or chain complexes in the chambers of Y cut out by the wavefront hypersurface of lambda.
The title is wrong. The title is three dimensions. There's only one three dimension.
Three dimensions.
This is S. Three dimensions.
So that's correct.
Three dimensions.
Yeah. 1 dimension, 2 dimension, 3 dimensions.
That is three dimensions.
I grew up speaking,
Okay, sorry.
but
English not like Chinese. Suffix is not.
okay. So some chain complexes in each chamber, some maps on the walls between the chambers, and some extra conditions at double points and at singularities of the hypersurface. And there are two topics that I didn't get to. So, okay, one is called microlocal monodromy. And one is called fillings, or Lagrangian fillings. So, microlocal monodromy this is trying to be a functor from this category to local systems on the Lagrangian. So that microlocal monodromy. And trying to be because these are usually some kind of twisted local systems. Twisted by Maslov stuff. But in any example that I'll talk about today, that won't be an issue. Will just be a genuine functor from this category associated to the Lagrangian to derived category of local systems on the Lagrangian. You can give the definition in an example. So if lambda belongs to the co-circle bundle over R2, and it's front projection looks like this. Okay, and it should be co-oriented. So these mirrors all point out. So so an object of this category and to label every chamber of R2 by some chain complex, let's just put 0 outside in the non-compact part to make it a little easier. And then there will be a chain complex in each one of these little little regions surrounding this star, and then the chain complex in the middle. And then there's some maps like this. So it's the data of a 6 chain complexes and 5 maps. And they should obey some conditions. Well, there are no singularities of this wavefront, so we only have to talk about these double points. Each one of those 5 crossings, there's a condition, which is that this square should be exact, which amounts to saying that when A1 and A2, or AI and AI plus 1, are labeling adjacent little bubbles here, the induced map here should be an isomorphism. Okay, so now you can define this functor to local systems on lambda. Well, what does lambda look like? It's chopped up into 10 pieces here, right? Let me name them with Roman numerals. So here's piece 1, piece 2, piece 3, piece 4, piece 5, piece 6. So lambda okay. Here's lambda cut up into 10 pieces. Each one of these intervals on this circle is like something like that, or something like that. So it labels a wall in this wall and chamber decomposition of R2, and that wall has a map on it. So like on this Roman numeral 1 wall, there's a map from 0 to A1. So, so I'm going to put A1 there. And on this Roman numeral 2 wall, there's a map from A2 to B. I'm going to put the cone on that map on this Roman numeral 2. Which maybe I'll write as B divided by A2 for short. Um, okay, so Roman numeral 3 is another outer wall. There's a map from this 0 to A3. The cone on that is A3. Can we keep going like that? When we get to the 10th wall, I guess that's B divided by A5. And here we're back to A1 again. So this condition says that if I take the map from AI to B, and I compose with the projection to B divided by AI plus 1, this should be an isomorphism. So there's some kind of natural isomorphism from here to here, and here to here. And by the time you get back, you might have picked up some monodromy. So this is the data of a local system on lambda. So this is the microlocal monodromy local system. So do something similar in general. You never run into trouble at double points. At singularities, like at a fold singularity, you might not have this chain complex isomorphic to this one, but to a shift of this one. And that accounts for, well, some trouble.
Does that give you a derived category of complexes instead of complexes? Or?
It's everything is inside is derived.
Sorry,
Yeah.
because this is an actual honest local system.
I guess
once you
this-
get these double points,
Even, I mean, this will be some chain complex of local systems.
just in this example.
In this example, well,
An honest local system.
what I'm worrying about is that it could be that this monodromy around the circle would not give an isomorphism between A1 and itself, but an isomorphism between A1 and some shift of itself. And that would be a different kind of
Thank you.
object. Well, okay, so, but in particular, the cone on any one of these maps has the same isomorphism type, for example, the same dimension if it's concentrated in a single degree. So it makes sense to single out objects of microlocal rank 1, let's say. So I'll call that maybe M sub 1 of lambda. So if an object here is microlocal rank 1, then that means when I take the cone on the map from 0 to A1, I get something one-dimensional in degree 0. So all of these, and similarly for the map from 0 to A2, so all of these A's have to be one-dimensional. And then the B in the middle has to be one more dimension. So the cone on this red map should be, from A to B should be one-dimensional. That means B should be two-dimensional. So in this example, an object of M1 of lambda is, well, maybe I can fix this B fix B to be maybe C2. And then each one of these AIs defines a line, and that's C2. These should all be injective maps from some line into C2. And then they should be subject to the conditions that A1 is not the same as A2, which is not the same as A3, which is not the same as A4, which is not the same as A5, which is not the same as A1. So this is a algebraic variety. This is a space of 5 points on P1, 5 ordered points on P1 that don't kind of, I mean, some of them are allowed to coincide. A1 is allowed to be equal to A3. There's no crossing that forbids that from happening, but any two adjacent A's are not allowed to coincide. And then I should maybe take isomorphism classes of objects in this M1 lambda, divide by the PGO2 action. And this becomes a famous surface. It's a Del Pezzo surface of degree 5 with an anticanonical divisor taken out, minus an anticanonical pentagon. So, well, and for what it's worth, there's a microlocal homological map from here to local systems on lambda. That's local systems on the circle of rank 1. So this is some Del Pezzo surface. This is some C star, and this map is just constant. It can be more interesting in general, but in this case it's just going to be take the value 1 everywhere. So let me try to explain why. So Lagrangian feelings. So what are one or maybe one source of points in the space M1 of lambda. So lambda lives in this cosphere bundle over Y. Well, our some Lagrangians in the symplectic manifold, the potential bundle of Y, with boundary on lambda. This is the Nadler's acyclic construction. So you take your Lagrangian and P star Y. Maybe I shouldn't have erased that picture. It's not quite the same one, but and you want to define a sheaf on Y. So sheaf on Y is the data of at least a chain complex in every region of this hypersurface, or the complement of this hypersurface. So those are called fibers. And what they are, in this Nandler-Zaslow construction, are that they're Floor homology groups, or maybe Floor chains, of this Lagrangian against the fiber at a point, at this blue point. Y should be the should be the Floor cohomology of this Lagrangian against a cotangent fiber at that point. Well, okay, so it takes some work to define these Floor groups. When it so lots of things could go wrong when trying to define them, but when it's defined, you can actually define some twisted version of this, where I put a unitary local system on this L. And if that local system has rank 1, the resulting point of M1 of lambda will have microlocal rank 1. This gives a map from the space of unitary local systems on L, which is some torus, to M1.
So these Floor chains are morally just in the simplest way, just intersections of L with these vertical fibers, with signs.
So
and
it's usually some
things.
finite set, maybe, and
all of you're lucky, right?
Right, and all of the interesting stuff is actually going to happen when you try to define these red maps between them, and then you'll be looking at, some kind of a infinity structure on these groups to define those red maps. And
this will just depend on the chambers as opposed to the actual point Y, or
it depends just on the chambers. Well, if you the flavor of Floor cohomology that you use here is, I guess, called unwrapped. And it will depend only on the chamber that lies in, up to, well, like out here, it could happen that in the sense that it gives a local system on each chamber.
right?
Yeah, they vary in a locally constant way on the chambers.
You can just pick a point and say that's your A, and then the others are isomorphic to it, and so.
Right.
By the way, let me back you up.
Yeah.
You jumped from M of lambda to M1 of lambda. Is there some way in which M1 of lambda generates M of lambda, or?
Oh, C of lambda, you mean?
Sorry. Yeah.
No, it does not generate it for the same reason that, like, rank 1 local systems on a surface don't generate all local systems on a surface or on any manifold. But
Yeah, of course, that's part of it.
so, I mean, so this Lagrangian L is is exact, you can analytically continue this map from this compact torus to an algebraic torus. And for this, you don't need floor theory. So you can cook up something just using topology wavefronts. That'd be worse. I was writing yesterday. So, because if L is exact, it has a wavefront in y times r, which will sort of be related to the boundary on the wavefront of lambda on the side of y and visible as a slice. Let me draw an example of that. So this Lagrangian lambda is a filling. Well, if I take a very general exact filling, I can look at its wavefront and it will look kind of crazy. But in this example, you can conjecturally always take some exact Lagrangian isotopy so that it will look nicer. And for example, it should look like this. Okay. I'm going to draw a tree with 5 leaves first. And then draw what should happen out here. Okay.
So lambda is in T infinity.
Lambda is in T infinity of y, and the wavefront of lambda, or just the projection, or I just mean the projection of lambda to the base of that sphere vibration. That's what lives in y. So that looks like this.
Oh, the wavefront of that.
Yes, the wavefront of lambda looks like this, and there will be some filling of it whose wavefront looks like this. So this guy is co-oriented with this. These guys are co-oriented kind of upwards. I don't know if that picture is popping out at you in 3D, but it's a surface immersed into R3. You have some smooth portions of it away from this blue location, and then these blue points, it's immersed, and then where the blue points meet at a trivalent vertex, well, that's some kind of place where it's not immersed. That's a wavefront singularity. It's not a generic. Well, I'll say more about it in a second.
It's a ciphered surface for that particular.
This is a surface in R4. So do you call that a ciphered surface?
No,
It's
not.
but it is a genus 1 surface. So this is some drawing of a genus 1 surface with one boundary component. The boundary component is out here.
And then it's immersed in this.
Yeah, yeah.
Not quite.
So for this kind of wavefront, so you can study sheaves on this wavefront. You can study C of L. By thinking of it as a Legendrian in T infinity of y times r. And theorem
C of L is what? Is the wave?
C of L is the category of sheaves, in this case on R3, that have singular support in this wavefront, or in the Legendrian lift of this wavefront. So there's a pretty tight dictionary between exact Lagrangians at least in R2n, and the Legendrians in R2n plus 1. And it's a theorem of with some elaboration by Shinjin and myself, that this microlocal monodromy functor from C of L to local systems on L is an equivalence.
That was not true for the lambda.
So it's not true for lambda, right? So what makes this work is that this Lagrangian, this L has a Legendrian lift, which then has a Lagrangian projection, and that Lagrangian projection is embedded. So so you can make this definition for a immersed Lagrangian filling of lambda, and this would not be true anymore. So this is true when L T star of y is embedded. And then because of this, you can write down this map that I'm erasing. So you get a map from M1 of L to M1 of lambda by kind of taking a sheaf on this R3 and restricting it to the boundary of the picture. And this will be an open map. So for when lambda is not, sort of in general. This is an open embedding. So some embedding, in this case, of C star times C star is the homology of this genus 1 surface with C star coefficients into M1 of lambda, which in this case was some delta surface. So you can use this to give a this map is some kind of invariant of that exact Lagrangian. So if I had built this picture by starting out by drawing that tree. So if I had drawn a different tree, like this one, this would give a different map. From C star times C star into the Stelknitzer surface. And so because of that, these two exact Lagrangian fillings, they can't be Legendrian isotopic by this theorem, Kashiwara-Shapiro theorem.
Sorry, can you say that again?
So these, I've drawn maybe a little carefully here and sloppily here, the wavefront of two different exact Lagrangian surfaces. And they're not isotopic to each other through Legendrian surfaces. Did I say two exact Lagrangian surfaces? And they're not exact isotopic to each other
Because they're different maps.
because they lead to different maps into the Stelknitzer surface. Well,
See, essentially because the local system is different.
because the constructible sheaves are different. So the local systems look the same, at least they're both just C star times C star on each torus.
But they fit in.
They fit into this moduli space of constructible sheaves in a different way, in two different ways. So, this talk has already been talk is mostly presenting old results of Kashiwara and Shapiro, but the rest of this is joint work with Eric Zaslow and Lin Shen. So we have this idea that it would be fun, the building block of that example is this trivalent vertex, right? So this is this Lagrangian disk, or the wavefront of a Lagrangian disk, embedded in R4. The wavefront is immersed in R3. It has this wavefront singularity at this trivalent vertex, which is not generic. So it's possible to kind of push three swallowtails out of this trivalent vertex, either on the top or on the bottom. So it's what Arnold called a bifurcation of fronts. In low dimensions, there's a classification of bifurcations of fronts, and this one is called D4 minus. It's kind of the critical front of this D4 minus bifurcation of fronts. Okay, and so you can kind of paste them together to build interesting Lagrangian fillings of Legendrian knots. And you can also paste them together in kind of around a sphere, so that you would get something without a boundary. So I give you a graph inside of S2. That'll be like this blue tree. This graph inside of S2. And every vertex has degree 3. Okay. Well, first just a little combinatorial fact. These are called cubic planar graphs. So we'll have some number of vertices, some number of edges, and some number of faces. I know the cube is an example. Embedded in S2. And the number of vertices is always going to be 2g plus 2. The number of edges is always going to be 3g plus 3. The number of faces is always going to be g plus 3. For some integer g. And you can use it to build this kind of wavefront in R3. So you can glue G4 minuses together in the shape of this graph gamma to get a surface of genus G. You just write S sub, well, let me write lambda. Lambda sub gamma into R3. So around this cube, you'll have this, maybe from far away it just looks like a sphere embedded in R3 in the usual way. And then when you zoom in, you see that the sphere actually has two sheets, and they're kind of crisscrossing each other in this fashion around the sphere. And it'll be an immersed surface, and the double points will look like this graph gamma. So this could be like a local piece of one of these things that I'm talking about. Okay, so that's a Lagrangian surface. Well, that's the wavefront. That's a family of wavefronts of interesting Lagrangian surfaces of genus G in, well, T infinity of R3 might as well be S5. Now, you can study, so I'm going to call them lambda sub gamma. So they're kind of three-dimensional versions of this picture, which is some wavefront that's wrapped up around the circle instead of a two-sphere. So you can define this category of sheaves on R3 with singular support in this lambda sub gamma, and it will contain this moduli space of sheaves of microlocal rank 1. And this is easy to describe. So a point in here is given by, well, there'll be some central region inside the two-sphere, which should be labeled by a two-dimensional vector space. And then in each one of these bubbles around it, there should be a line. So the point in here is given by G plus 3 lines in C2. But then there are conditions. So maybe a two-dimensional vector space is down here. And in between any two of these sheets, I have some line. But now, when these two lines are adjacent to each other across a blue edge of this graph, those two lines should be different from each other. Well, if L not equal to L sub F not equal to L sub F prime, when F and F prime are adjacent faces. So in other words, it's a coloring, a constructible sheaf of microlocal rank 1 is a coloring of this map. So maybe it's a coloring of the planar dual graph. Depending on how you define coloring, fate of the faces of gamma, not the vertices. With the property that two adjacent faces should have different colors, the colors chosen from P1. Maybe should divide that by the PGO2 action. So this some open subset of P1 to the G plus 3, so divided by this PGO2 action, it has dimension G. So, well, what are some things you can do with these constructible sheaves? So, here's one of them. So suppose gamma and gamma prime have different chromatic polynomials. So the value of a chromatic polynomial at n is the number of colorings of the faces with at most n colors. So if n is q plus 1 and q is a prime power, this will be the number of points in this moduli space that are defined over the field of Q elements. And maybe I better multiply this side by multiply or divide this side by the order of PGO2.
Yeah, I think the definition is.
Say what again?
The definition is.
The definition of this chromatic polynomial.
Yeah.
It's its value at n is the number of colorings of the faces of the graph with n colors, at most n colors, such that two adjacent faces have different colors. So suppose that this is true, well, then you'd have two different moduli spaces. Then these moduli spaces couldn't be the same. And then, so there's a conclusion. Then lambda gamma and lambda gamma prime are not Lagrangian isotopic. Oh, okay. So that's the kind of theorem that people value for Legendrian knots more than Legendrian surfaces. But in particular, all of these Legendrian surfaces, they have the same classical invariance. If you look at their Lagrangian projections, which are immersed, they're actually all Lagrangian isotopic to each other through not necessarily exact Lagrangians. So whatever you would mean by classical invariance of a Legendrian surface, these all have the same, but they're different from each other. Let's see, what's another thing? Here's another one. Suppose that a graph gamma does not have multiple edges. then this lambda sub gamma, which belongs to T infinity of R3, has no exact fillings into R6 in P star R3. The reason for that is that this, well, so when you have an exact filling, when L in R6 is exact, it gives you this map from, H1 of L. So this would be some 3 manifold with boundary on this genus G surface. You get this map from H1 of L, well, with C star coefficients, but it could also be FQ star coefficients into this moduli space. And that number of FQ points on this moduli space. So this has, and this should be some open embedding, and this is just going to have more points than this for a graph with no multiple edges. You can count these bound what the size of that chromatic polynomial is, and it's just smaller than, this would be like q minus 1 to the g. So there's not any space in this moduli space for there to be an exact Lagrangian filling. So this fact kind of weirded me out for a long time. Maybe more experienced Fukai category folks wouldn't have been weirded out, but like I've been thinking of this space M1 of lambda. You know, when lambda was a knot, I'd been thinking of it as a moduli space of Lagrangian surfaces, maybe decorated with some local systems. And here was a case where you had this beautiful moduli space with no, but they didn't seem to be coming from any Lagrangians. So what is the symplectic geometric meaning of this space in such a case? Where are the points that one of them are coming from? So more about that in a second. But I still have 5 minutes, or am I?
Less than 5 minutes.
Less than 5. Well, okay, maybe. Maybe I'll just mention one more thing and stop. So let's talk about this microlocal monodrome map. So maps the space of colorings of this graph to the homology of its surface. It's kind of, this is the space of with C star coefficients, the space of local systems on this surface. And it's kind of a combinatorially an interesting map. So what is this map? So I take a sheaf, which is given by all these lines labeling each region here. Let's just call it, okay. In this case, there are 5 of them. And an edge of this graph, it's a double point locus. So it's actually, it lifts to a circle in could go on for a while, but there's some circle here whose projection in this wavefront will be one of those edges. And the monodromy around that circle, you can compute it. The microlocal monodromy around that circle in terms of these lines, it's the cross ratio, or minus the cross ratio. So monodromy around these blue circles, microlocal monodromy. This is some G-dimensional space, some 2G-dimensional space. And this is a Lagrangian embedding, and it's one that, I mean, has shown up before, and I mean, I'm not sure I remember. I think Demofte, Gabella, and Goncharov at least have considered, for slightly different reasons, a similar, or an identical, more general Lagrangian embedding of the space of colorings. And so you have this holomorphic Lagrangian and this holomorphic symplectic manifold, and it's doing some Donaldson-Thomas thing or some open Gromov-Witten thing with these possibly, well, Lagrangian fillings of this surface. Sorry, I'm out of time. I'm over. Okay.
Questions?
So why is it always rank 1 for the Lagrangian fields? Why the microlocal rank is rank 1?
Why did I stick to that case?
No, I mean.
Well, he only considered those.
Okay,
Yeah,
because you have a map, right? You're mapping to rank 1.
We were strict to those with vector.
Well, if you put a rank 1 local system on your Lagrangian, then you get something of microlocal rank 1. If you put a more complicated local system on your Lagrangian filling, then you would get a sheaf with more complicated microlocal behavior.
So the Lagrangian filling always hit the cotangent fiber at only one point.
Say that again?
Is it true? The Lagrangian filling always hit the cotangent fiber at one point. So
no, but that's true close to the boundary. It's true close to the boundary of this Lagrangian filling.
We can continue. Stop. Other questions?
No other question. Lecture. My lecture has to stop. You cannot.
Oh, okay. No question.